Hello, everyone. The paper I'm going to talk about is task modifiers for HTN Planning and Acting. My collaborators are Dr. Munoz-Avila and Dr. Hu from Lehigh University,
Hello,
and
baby.
Sampath and Surabia and
Rehan is presenting now, and you have to be present for the question that we can talk. Film some
I'm
minutes.
sorry, what happened?
I think someone forgot to mute his or her mic. You can
The
continue.
open world.
Okay, I will continue. The other collaborators are Sampath Surabia and Dr. Cox from Wright State University. So first, I'm going to describe several key concepts in HTN planning. Our approach is based on these concepts. The first concept is tasks. A task consists of a name and a list of arguments. So, for example, the root task here is transport a package from location 1 to location 2. A task can be either primitive or compound. Another concept is method. A method, in this case, we define it as a function that receives a state and a task and outputs a task list. A function defines when and how to decompose a compound task into its subtasks. The other concept is actions. An action, we also define it as a function that receives a state, a task, and outputs a new state. So in this case, the function defines what would the next state be. And the primitive task, instead of decomposed by a method, it is accomplished by actions. And an HTN planning problem consists of a state, a task list, specifically the agent's task list, and the domain that includes a set of actions and methods. A plan is a sequence of actions. A plan is a solution if the first task is primitive and the first action in the plan is applicable, then we check again whether the remaining actions is a solution for the new state after applying that action and the remaining tasks. And if the first task is compound and there exists an applicable method, then we replace the first task with its subtasks, and then we check whether the plan is a solution for the new tasks. So essentially, a solution is defined cursively. So those definitions are the traditional definition in HTN planning. However, in some problems, the domains have certain characteristics that are not the same as the traditional domains. So one of the most important aspects of this is the agent cannot fully observe the environment state. So the environment is external to the agents, and the agent still has a set of methods, but instead of knowing the action functions, the agent only knows the actions names. So, and also the agent needs to observe a state through observation. So that means the dynamics of environment is not fully known to the agents. And in this case, dynamics of environment is referred to the action functions. So the cycle begins by with the agent observing a state, and then the agent takes an action. This will cause the environment to have a state change, and then the cycle continues. Because from the agent's perspective, the dynamics are unknown, so the state change could appear as some unexpected events. And to handle this type of situations, we describe a simple mechanism called task modifiers as an extension to the HTN framework. So originally in the original HTN framework, an agent task list can only be modified in two ways. And this relates to the previous definition of a solution to a problem. So if the first task is primitive and there exists an applicable action, then after applying that action, the task list will be changed into a new form where the first one is removed. And if there exists an applicable method, then the new task list would have the subtasks of that method to replace the first task, and then the rest of the tasks. And task modifier, the extension we described, provides another way to modify the task list without making any significant changes to the definition of methods. So we define a task modifier as a two-argument function that receive a state and task list and outputs a new task list. If the new task list is the same as the original task list, we consider no modification has happened. So the definition of a task modifier is abstract. This means that any function that receives a state and a list of tasks and then outputs another list of tasks can be considered as a task modifier. And the implementation is depending on the programmer. Task modifiers provide an additional way to modify a task list, and instead of compare with methods that only receive a single task, task modifiers receive a task list as input. This means that task modifiers are more general than methods, and it provides greater flexibility for implementation. Now we show an algorithm that is based on SHOP and integrates a task modifier and interleaves planning and execution. The main differences between the original algorithm and this algorithm are underlined. The main addition to call task modifier is on line 12, and on line 2 and lines 10 and 11, the code provides the capability for the agent to interleave planning and execution of actions. And the algorithm, similar to the definition of task modifiers, does not specify how to implement the function itself, but rather it just offers a way to utilize this mechanism based on the SHOP algorithm. And we did some preliminary experiments to evaluate an implementation of a task modifier. So one of the domain is a marine vehicle simulation environment. And this domain has some of the characteristics described in the previous slide about having certain unexpected events that the agent needs to handle. So in this environment, at the start of each episode, there are some transport ships on the left, and they will move from left to right. There is a pirate boat and 3 fishing boats. The pirate boats will move randomly in the central region and placing mines along the way. If a transport ship encounters a mine, it will be destroyed. The agent does not know the identity of the pirate or the locations of mines. And we use this domain as a proof of concept to show that it is feasible to implement a task modifier and provide a certain level of performance. So we implement an agent that has a predefined task modifier and a baseline that has a random task modifier function which randomly outputs a new method. And the result shows that the agent, this approach is feasible, provided that we providing the required knowledge to the task modifier to handle the unexpected events. So in summary, we describe an extension to the HTN planning framework called task modifiers as a solution to a certain type of domains. And we describe an algorithm based on SHOP that integrates task modifiers and also interleaves planning and execution. And in our preliminary experiments, we demonstrate that this approach is feasible. For future work, we want to explore two areas. First, we can define that an assignment from the task modifier function as a modification similar to the original definition of methods, and therefore there may be a way to unify the definition of methods and task modifier into one. And the other thing we want to explore is that given a definition of each modification, and each modification contains the list of conditions, as well as the task modifier itself as a function, it can select the appropriate modification based on certain criteria. Then we would like to know the ways to learn the criteria, therefore reducing the amount of human engineering required to have efficient task modifier. So that's all. Now I will answer your questions.
Great. So we have like 30 seconds left. I typically would raise my hand like when you have 1 minute left. So I don't see questions on chat and Slack. I do have one question myself though.
Okay.
So this process, when you're saying some of the actions, you may know the name, but you don't know how the action works. Have you sort of, or in your implementation, is it compatible with adding a reinforcement learning mechanism for learning what that action do over time and then turn that action into a known action?
I think the definition that we use for as a motivation for this type of problem is, so this is inspired by reinforcement learning, and we can use reinforcement learning to learn some kind of policy that directly selects actions given a state. So that's one way to look at this problem. But we also, in this case, want to, based on the framework from HTN, and therefore it means that we don't. So basically, that means we need to consider the other concepts such as methods, and therefore, okay. I think from
we're running out of your 30 seconds. Sorry for the interruption. We should move on to the next paper, and then we'll keep all of this discussion in the breakout room.